names here. And much of that work covers both statistical and algorithmic issues. Right, and so we'll sort of divide the talk into statistical issues and algorithmic issues. The type of statistical issues we have to address are how well can nearest neighbor perform? And more precise questions are, when is one nearest neighbor enough? Or how many nearest neighbors should we use? What values of k should we use? Is there a curse of dimension? We've all heard that nearest neighbor incur some sort of curse of dimension. Is there always a curse of dimension? The algorithmic issues are essentially how efficient can we implement nearest neighbor? Which data structures to use? Can we parallelize nearest neighbors? They tend to be somewhat hard to parallelize. But can we parallelize nearest neighbors? And if we do all these things, what do we trade off? So those are the questions addressed by a lot of the theoretical literature on nearest neighbor. And we'll try to sort of synthesize much of this work through various intuition. The first intuition that comes out of this type of work is that data representation is very important. If you want to understand the statistical issues have to do with how you represent the data first before you do nearest neighbor procedures. And examples of, and if you want to understand even the algorithmic issues, it has to do also with how you represent the data. So the first examples of representation, we all know, the first simple example is you just use a Euclidean metric. So you take your data, it's a vector in some Euclidean space, and you just use it directly. Some new type of representations come from deep neural net, where the use with deep neural net will be you take the last layer of a deep neural net, and then you do nearest neighbor on that layer. Or you have word embeddings, you embed the words into some space, maybe word2vec, and then you do nearest neighbor in that space. The point of view that we are going to take is the following, is that representation, once you represent the data and then maybe you represent it into a Euclidean space and you're using the Euclidean metric in that space, then representation is really just equivalent to a choice of metric. You can view it that way. It's just equivalent to a choice of metric. And so the point of view we'll take is, how does the metric influence all the questions that we are caring about? How does the metric influence statistical accuracy? How does it influence the search? Right. So we'll see that actually particular properties of the metric would influence this key aspect of nearest neighbors. The outline of the tutorial will be the following. In the first part, I'll discuss basic statistical insights. And I'll start from the 50s. And move on to today. So basic statistical insights. And then in the second part, Sanjoy will cover more refined analysis. And the two parts are sort of related because you sort of need to understand some of the basic statistical insights to get into the hardcore stuff that Sanjoy will be presenting. And Sanjoy will discuss also much issues having to do with implementation and trade-offs and such things. All right. So, basic statistical insight. The basic statistical insight starts with the universality of nearest neighbors. So the first question is, we know that nearest neighbors are non-parametric methods, and we've all heard that they sort of can fit anything. And I'll start with that, and why can they fit anything, and in what sense can they fit anything. And then from there, we'll get into more recent results. So KNN, as a universal approach, it can fit anything, but provided that you let the number of nearest neighbors grow, but not too fast with sample size. So as the sample size increases, you have to let the number of nearest neighbor grow, but not too fast. And I'll become a bit more precise soon. And to make it more precise, I'll just take the case of regression. However, much of the intuition will be true for classification also and for density estimation and such. So let's consider the case of nearest neighbor regression. So first I'll define it. Here is some cartoon of a regression line, some function f that we want to fit. We assume that the function f, we assume that we obtain y, the label, as the function f plus some noise. F is unknown, we have ID data, so it's a simple classical regression setting. So how do you do nearest neighbor regression? I'll define the nearest neighbor regression estimate at a point x as fk, and fk is nothing more than the average of the y values of the nearest neighbors of x. So if x is here, I look at the nearest neighbor, and I average the y values and return that as an estimate of f. So that's a simple nearest neighbor regression. And KNN is universal in the following sense, in the sense that fk, as the sample size increases to infinity, fk approximates f in expectation. Now, fk approximates f in expectation as long as k over n goes to 0, and as long as k goes to infinity. So those two conditions are quite important, and I'll explain in a second why those conditions are important. The key point here is that we don't make any assumption on the f. F can be any function, no matter how complex. Fk would eventually approximate f as long as these conditions hold. So why is that? The basic intuition is as follows. I'll try to go through it slow. Let's consider again this cartoon. Here is x. Here is its nearest neighbors from the sample. And now I'll denote the nearest neighbors xi 1 through k for this x. And consider the following. This is a sample of a particular size. The nearest neighbors are so far from x. If I increase the sample size, then here I'm fixing k, the 3 nearest neighbors get closer to x. That's the first point. As the sample size increases, intuitively, your nearest neighbor gets closer to you. Okay? So if I fix k, if I let k fix, this will hold. You can imagine right away that if I let k be infinity, it will not hold. The nearest neighbors will be very far. But if k is fixed, then as I increase the sample size, the nearest neighbors will get closer. And in fact, as long as k does not grow too fast with respect to n, then we'll have this property that the nearest neighbors get closer. And that's where we're getting this condition from, the condition that k over n need to go to 0. We want the fact that the nearest neighbors are getting closer to x. Now, suppose that the nearest neighbors are getting closer to x as the sample size is increasing, and suppose now that f is continuous. Then by definition of continuity, the values of f at the nearest neighbors will get closer to the value of f at x. That's just the definition of continuity. The points are getting closer, so the value of f at these points are getting closer to the value of x. So we are one step closer already to the universality result, but we've assumed so far that f is continuous, but that's fine. Now, this is the second condition. K needs to go to infinity. Why? Because the fk is defined as an average. It's defined as an average of y, and y is just f of xi plus noise. Y is just xi plus noise. So we are really just averaging f of xi plus noise. We just say that f of xi is getting close to f of x, and the averaging effect removes the noise. That's the full intuition, right? And it's some form of law of large numbers. That's not exactly the law of large numbers, but some form of the law of large numbers. As k grows, then this thing is eventually just goes to f of x, which is the values that these things are going to. So that's the key point of the universality, but so far we've assumed that f is continuous. In order to remove that, there are tons of results in function approximation theory that tell us that any function, no matter how arbitrary, can be approximated arbitrarily well by a continuous function. So you sort of repeat this sort of argument with approximations to this function, and then you get the universality result. So that's the high level of why nearest neighbors are universal. Here we did it for regression, but the same is true for classification. It's universal for classification. Any classification function can be approximated eventually, as long as you have these conditions. So that's the first big message from this tutorial. And I put it first because I felt like, okay, everybody should know or should have some intuition of this. Much of these results started very early. The seminal results started in 51 by Fix and Hodge for classification plus some regularity conditions. And then eventually Stone removed much of the regularity conditions and was able to get it for any function. the universal consistency of nearest neighbor. And eventually also there were results for density estimation, regression, and such. So the main message here is that nearest neighbors are universal. Are universal as long as k grows with n, but not too fast. So one point here right away is that one nearest neighbor is not consistent. If you fix k, you cannot approximate every function. At some point, no matter how much you're increasing the data size, if you fix k, eventually you saturate, your error will saturate. So you sort of need these conditions. And one simple setting of k that satisfies this condition is k equal to log n. Approximately, you'll satisfy these conditions. But this is still giving us just sort of a rough intuition as to how to set k, right? And we want to have a more refined picture as to how to properly pick k. So in order to get that more refined picture, I'll start with trying to understand the behavior of nearest neighbor distances. And by nearest neighbor distances, I just mean how far the nearest neighbors are from the point. Because in order to even get the universality results, that's why we started with, we try to understand how far the nearest neighbors were from the point. And here's another reason why we want to start with nearest neighbor distances, trying to refine our understanding of nearest neighbor distances. Recall the intuition, the working intuition. Why do nearest neighbor work? They work if the closest neighbors of x are mostly of similar type as x, similar type y as x. Okay? If the closest nearest neighbor are of similar type, and so you sort of are warning that the nearest neighbors of x are close to x. So first we want to understand, are they close to x? How close can they be to x? Formally, let's define Rk of x, this simple quantity, as the distance from x to its kth nearest neighbor in IID data. And we want to understand this quantity as a function of the distribution, as a function of KNN. All right. So here is a basic intuition again. Let's look at this cartoon. These are the three nearest neighbors of x. We'll assume that all the xi's are ID with some density px in a Euclidean space Rd. And now let's consider this ball. I'll call it Bx. And the ball Bx is just the ball containing the smallest ball containing the k nearest neighbors. And understanding Rk of x is just on this. Remember, we want to understand Rk of x. So we really are caring about this ball, the ball containing the k points. It's Bx Rk of x. So first assume that there are no ties. And all I mean by that there are no ties, is that there are exactly k points in this ball, right? Then what that means is that the empirical mass of this ball is just k over n, right? Now, it turns out that with high probability, the empirical mass is very close to the true max under px, under the real distribution. What that means is that we have with high probability that px of this ball is approximately k over n. Okay? Now we can rewrite px of this ball using elementary definitions of the mass of a ball. Px of this ball is just the integral over the ball of the density of x. Now suppose that suppose the ball is small. Suppose the density is not changing too much, right? If the density is not changing too much, then px of x prime is essentially px of x. I can pull it out. And so px of bx is just px of x times the volume of the ball in Rd. The nice thing here is that the volume of the ball in Rd, we know that it is approximately, the ball is of radius Rk. The volume of this ball is approximately Rk of x to the d, to the dimension of the space. So now what we have is px of bx is approximately equal to this, px of x times Rk of x to the d. So Rk of x is appearing. This is what we want to analyze. Rk of x is appearing here. And it gives us this equation, px of x times Rk of x is equal to k over n. So now we've characterized Rk of x. So just invert that equation and you get this. You get that Rk of x is approximately 1 over px, k over n, 1 over d. Much of the analysis of nearest neighbor methods goes through these procedures, goes through the same sort of intuition, characterizing RK of X, understanding how the nearest neighbor distances behave. And here you just get how it behaves through simple intuition. So now let's try to understand what this equation tells us. So the immediate messages we have is that if I let Px go to 0, RK of X increases. And that's an intuitive message. If the density is very low in some regions, your nearest neighbors are very far. So that's very intuitive. A less intuitive message is the following. Suppose that this quantity is less than 1. So this quantity will eventually be less than 1 if the sample size is large enough. Suppose this quantity is less than 1, then you can see that as the dimension of the space increases, RK of X has to grow, has to go up. So that also goes back to some common thing people tend to say, that in very high dimensional spaces, points are very far from each other. And you're getting that from here also, that as the dimension is increasing, the RK, the distance to your nearest neighbors, are increasing. So what does that tell us? It tells us that in some sense, in high dimensional spaces, we sort of want to use smaller k. By using smaller k, we counter the effect of the dimension maybe. And so maybe in higher dimensional spaces, we want much smaller values of k. So that's one message, but we'll verify that message a bit later. One other message we get here right away is the curse of dimension. The famous curse of dimension for nearest neighbors. So how do we see it? Suppose you want RK of X to be very small, let's say this small. Suppose you want RK of X to be very small. Then you automatically can see by just inverting that you need n to be exponential in the dimension. So that's the behavior that you're getting. So dimension has this effect. However, fortunately, little d does not have to be the dimension of the data. So that's a big message that I'll try to give some intuition for. The little d here does not have to be the dimension of the data, but we'll view the little d as some sort of effective dimension. Why? Because in order to obtain this equation, all we had to do was, if I go back a little bit, in order to obtain that equation, we went through this computation. We went through this argument. So the argument really boiled down to Px of Bx being approximately RK of X to the d. So here we'll say essentially that the effective dimension of the space is whichever quantity satisfies an equation of this sort. And it turns out that even if X is in some high dimensional space, the quantity that satisfies an equation of this sort might be much smaller than big D. And I'll give some intuition in a second as to why. It turns out that this quantity, little d, is really a function of your choice of metric, and it's also a function of where X lies in the high dimensional space. You can already imagine that if X is in very high dimensional space but lies on a manifold, that the quantity that will satisfy this equation should not be so large, but we'll get to that in a second. So let's first give an example in terms of metrics. So suppose for now that X is in a very high dimensional space, but your choice of metric ignores essentially all coordinates but the first coordinate. Your metric is just in terms of the first two coordinates, let's say, right? Then the first thing you'll have to just ask is what does the ball in that space look like? When we say a ball, how do we define a ball? The ball in terms of this metric is all the points, the ball centered at X of radius R, is all the points that are distance at most R from X. Because the metric ignores this dimension and only cares about this dimension, the ball looks something like, somewhat like this. And you'll see right away that we again have the same property. This is a space, a cartoon space of dimension 2. However, if you look at the mass of this ball, let's say this side is 1. If you look at the mass of this ball is just R times 1, it's R. So the effective dimension of this is 1. So your choice of metric affects what the effective dimension is, and it affects your nearest neighbor distances. Now let's look at a second example. Suppose X is on some very high dimensional space, but lies on a d-dimensional manifold. Then consider again a ball B of radius r centered somewhere on the data space. Why centered on the data space? Because when you're actually doing regression or classification or any such thing, you are really just sampling from where the data lies. So you don't care about any other parts of the space, even though you don't know a priori. You're working in big RD, you don't know a priori that you're lying on a manifold, but you're only sampling from the manifold. So the only balls we are caring about are balls that are intersecting the manifold. Now, what is the mass of such a ball? The mass of such a ball will be an integral over the manifold, not an integral over the whole space. It will be an integral over the manifold. If the manifold is of dimension d, the integral is over the intersection of this ball and the manifold. If the ball is of, if the manifold is of dimension d, it's a little d dimensional integral. And so what you'll get in the end is that px of b is of the order r to the little d, not r to the big D. And again, the effective dimension is just little d. Okay? So the key message here is that irrespective of the ambient dimension, of the very large ambient dimension, Rk of x is going to behave in terms of the intrinsic dimension. And the intrinsic dimension is defined by the metric and by where the data lies in the space. So here is a quick simulation that everybody can do at home. I'm a very bad programmer, but I've done this, so I believe everyone can do it. So just pick data of very little dimension d, embed the data into some higher dimensional space, and increase the dimension, and compute the nearest neighbors. You'll see that the nearest neighbor distances will not depend at all on the big D. It will just depend on the small d. And here is a simple computation. Here are the nearest neighbor distances, it just stays stable. As I increase big D from 1 to 100, doesn't matter. Little d is fixed to 2 here. So the nearest neighbor distances just depend on the intrinsic dimension of the space as given by where the data lies and the metric that you are using. There are much refined analysis of nearest neighbor distances. I'll mention some of them. And much of these analysis tries to understand how nearest neighbor distances truly depend on the density of the data. But otherwise, much of the intuition is captured by what I just discussed. The implications are the following, hopefully, that now we know that nearest neighbor distances are not affected by the ambient dimension, but are affected by the intrinsic dimension of the data or of the metric. And so hopefully, nearest neighbor methods, which are essentially based on nearest neighbor distances, that nearest neighbor methods are also only dependent on the little d, not on the ambient dimension. But we'll have to show that, we'll have to prove that. And that would mean something very nice for nearest neighbor methods, since in a lot of practical applications, the intrinsic dimension is very small. If for documents, for instance, the intrinsic dimension will be the sparsity of the document representation. So, in order to now understand whether the fact that nearest neighbor distances are well behaved means that eventual procedures are well behaved, we'll look at regression and classification, and we'll try to establish rates for regression and classification. Much of the same intuition that I'll develop would also hold for similar problems. So we want to go from bound on Rk of x to error rate. The program of construction will be the following. I'll start with regression bounds and explain the basics of how we obtain regression bounds. And then from there, I'll get classification bounds by just reducing classification to regression through a simple sort of reduction. All right, let's go back to regression. KNN regression, remember, is defined a second ago. We are in this normal regression setting where y is equal to f of x plus noise. The KNN regressor is the average of y, the average y of the KNNs of x. Now, back to the original intuition, reformulating the original intuition as to when KNN works, the ideal metric row should satisfy something like this. If 2 points are close on the row, then f of x should be close to f of x prime. If x and x prime are close on the row, f of x should be close to f of x prime. And one simple way to formalize this that a lot of people have used is to assume that f is Lipschitz. F being Lipschitz just means f of x minus f of x prime is essentially less than rho xx prime. Or lambda rho xx prime. For simplicity, I'll just let lambda be 1 throughout. You can see right away that this implies this, that if rho xx prime is small, then f of x minus f of x prime is small. So this is a simple way to formalize this. Our performance goal is the expected squared distance between fk and f, and that's the usual L2 risk that is often analyzed. So this will be the performance. So what we want is we want to understand how to choose k such that fk minus f squared is small. So we want now to characterize this error under this type of assumption. So the first step is a simple bias variance decomposition. And the bias variance decomposition is based on the following fact. It's a simple fact that everyone can show. The fact is the following. Let's consider a random variable z. And let's look at the expected distance from z to a fixed point c. To c is just a fixed constant. The expected distance from z to a constant can be decomposed as the variance of z plus the distance from c to the expectation of z, the square distance from c to the expectation of z. And this is just algebra. So from this fact, we'll get the bias variance decomposition. This is how we'll proceed. Fix x, fix some query point x, and fix the xi's. This is your data. Fix the xi's, but we'll let the yi's be random. For now, we'll just fix the xi, let the yi be random, and we define this quantity f tilde k of x, which is the expectation of fk under the randomness in yi. Okay? Now, this quantity, we'll use it to plug back into here. So, what this gives us right away is that e of fk of x minus f of x squared can decompose this way. All I did here is essentially let fk of x be my random variable z, and f of x be my c, my constant c. F of x is fixed. Fk of x is a random variable under this randomness. And by plugging that into this equation, you get right away that this is the error we wanted to bound, that this error is bounded by the variance plus this bias term. So in order to bound this, all we have to do is bound the variance separately and bound the bias separately. So how do we bound the variance? The variance is fairly direct to bound. Recall that fk of x is just an average of yi. We know how to compute the variance of an average, and the variance of an average will just be computed easily like this. And what we get in the end is that the variance of fk of x is about sigma squared y over k, where sigma squared y is the variance of each of the individual yi's. Okay, so that's a quick step. The variance of fk behaves like 1 over k. The bias, to understand the bias, let's first recall what f tilde k is. F tilde k is the expectation of fk. So I take the expectation of fk, I bring the expectation inside here. E of yi is just f of xi, because I assume that the noise has zero mean. So E of yi is just f of xi. So f tilde k can be rewritten this way. Now, the bias term looks like this. So I want to subtract f of x from f tilde k. If I subtract f of x from this, I can automatically bound it this way. Okay? So now, the next step is, now that I have this bound, the next step is essentially just using the fact that f is Lipschitz. Now I just have f of xi minus f of x. I use the fact that f is Lipschitz. If f is Lipschitz, this is bounded by rho xix. The xi's that I'm looking at are just the nearest neighbors of x. And we know that rho xix are all bounded by rk of x. And rk of x, we bounded rk of x earlier by k over n, 1 over d. So that's the analysis, essentially. Now we know that the error is the bias squared plus the variance. So we have about 1 over k plus k over n, 2 over d. And we integrate. So remember that to do this, we fixed x and xi. Now we have to integrate over it. So We integrate over it, and quickly we get this fact. We get that the error is bounded this way, 1 over k, plus k over n, 2 over d. This fact in itself is very interesting. It's interesting because it tells us right away that the choice of k induces a trade-off. Right? So let's look at this first term. As I increase k, this term is going down. However, this term is going up. Right? So right away there is some sort of trade-off because the error is the sum of these two terms. So you sort of expect the error to behave like this, to go down and go back up as k is going up. So there is a sweet spot at which you have to pick k. Some quick simulation will show you the same thing, that as you move in k, the mean squared error will go down and go back up, and you need to pick the right k somehow. So we can optimize this bound to get the right form of k. If we optimize this bound, we get that k needs to behave like n, 2 over 2 plus d, and then we get this rate. And this rate is known to be optimal. Okay? All right. This is essentially the best choice of k, but remember, usually we don't know how to make that choice because d is usually the intrinsic dimension of our data and of the metric. The good thing here is that it verifies some of our earlier messages that the best choice of k need to grow as the sample size grows, and also grows as dimension is smaller. The good news here is that if you just choose k by cross-validation, you can show that you get this optimal rate, which is a really nice simple fact. Here, I would like to point out something. Nearest neighbor regression is actually a very complex form of prediction. It's non-parametric. It has unbounded capacity, but what we just saw is that it generalizes. It actually generalizes at non-trivial rate. So that goes back a little bit to the point that often is made about whether overparametrization still allows generalization. And this is a case where overparametrization actually still allows generalization, so which is quite interesting to me. In fact, you can go even further. You can let k, rather than choosing a single k for your whole data space, you can let k be a function of the data points, of the query point. You can choose k, a different value of k, at every x, and yet still show that it generalizes at a similar rate as what we just showed. And if you think about it, now you have an algorithm where you're choosing k at every data point. So the number of parameters of this algorithm is infinite. You have as many parameters to choose as number of points in your space. However, you still generalize, which is quite an interesting fact to me. You can show similar messages on the generalizations of the Lifshitz assumption. And there are many such generalizations of the Lifshitz assumption. I won't go too much into them. The main thing is you might start by just generalizing the Lifshitz condition to a so-called holder condition. In the Lifshitz condition, we just had alpha is equal to 1 here. You might change that to any alpha. You might, rather than making this condition, rather than saying that f is Lifshitz, you might say that the derivatives of f are Lifshitz, the higher derivatives of f are Lifshitz and such, and that gives you higher order conditions. The key point to remember is that as these conditions, as alpha is going up, the problem gets easier. F, the right of the function f, gets smoother and gets easier to estimate. You can imagine that if f doesn't change too much, doesn't change too fast, it's easier to estimate. Unfortunately, there is one message here which goes a bit against pure nearest neighbor. It turns out, and this is, you can find references in a really nice book by Gyorfi et al. It turns out that if you let alpha grow large, you'll quickly see that the basic nearest neighbor that we do, its performance quickly saturates. It cannot take advantage of the fact that f is easier, of the fact that the problem itself is easy. It's actually really nice for problems that are hard, but when the problem gets easy, you hope that nearest neighbor would also have better performance, but not quite. So it turns out that in order to fit much easier f, more smooth f, you need to use either local polynomials. So here with nearest neighbor, we're computing local averages. Rather than compute local averages, you do a linear fit or a polynomial fit locally among the nearest neighbors. When you do that, then you can get better. You can get much better performance. However, that is very hard to do in very high dimension, and so I guess that's why nearly nobody does it. The other way to do it is by using particular forms of weighted nearest neighbor, and then you could also get better performance as your problem gets easier. So that's as much as I'll say for now about regression. I'll switch to classification now. And quickly, I'll just show that classification reduces to regression. So from all the analysis we just did on regression, we can quickly get rates for classification also. Okay, so what is nearest neighbor classification? Everybody knows. The only change I'm making in the setting is that y now, rather than being a continuous y, takes only these two values. For now, I'll just talk about binary classification, y is 0 or 1. Here, in this cartoon, let's say that these are the three nearest neighbors, and these are 1, and this is a 0. Okay? So the nearest neighbor classifier just takes the majority of the labels of the nearest neighbors. That's nearest neighbor classification. It turns out that taking the majority of the labels of the nearest neighbors is equivalent to doing regression first and then thresholding the regression. So to see this, consider again the regressor that I discussed earlier, fk of x, the average y of the KNN of x. Here, if I say this is 1, 1, and 0, if I compute the average y is just 2/3 here. And 2/3 is greater than 1, is greater than 1/2. And you can see quickly that the majority is really equivalent to just taking the average and asking whether the average is greater than 1/2. So in that sense, you can do nearest neighbor classification by first computing a regressor and then thresholding the regressor. So that's the simple reduction. And now the question that comes up is, okay, if the regressor fk of x is close to what it's estimating, I'll say in a second what it is estimating. If it is close to what it is estimating, then would it be that the nearest neighbor classifier is doing well, right? Can we reduce the error of nearest neighbor classification to the error of nearest neighbor regression? So the performance goal is the usual performance goal. We want the 0-1 classification error. Equivalently, rather than minimizing the 0-1 classification error, I can minimize this excess error, the classification error of HK minus the classification error of the best possible classifier. And usually we call it the base classifier. And I'll define the base classifier in a second. Okay. First, let's sort of understand again what FK estimates, the regression version of the nearest neighbor. FK is estimating this f of x. Fk of x, remember, is just an average of the nearest neighbors. It's estimating the expectation of y given x. And since y is 0 or 1, the expectation of y given s is just the probability that y is equal to 1 given x. It turns out that the best possible classifier just thresholds this f. The best possible classifier says 1 whenever f of x is greater than 1/2. In other words, it says 1 whenever probability of y given 1, a probability that y is equal to 1 is highest. Okay? Now, notice that the nearest neighbor classifier is just mimicking H star. Okay? So it's just mimicking H star. Now, let's look at this cartoon. Here is x. Here is f, which is probability that y is equal to 1 given x. Here is f, how it behaves over the space. Here is 1/2. The base classifier in all this region, f is above 1, so it will return 1. Okay? Now, as long as you can tell right away that as long as fk is somewhat close to f, then the value of h in this region will be the same as h star. So the excess error will be 0. Right? And in fact, more formally, one can show that the excess error is at most twice the difference between fk and f. In other words, if fk is close to f, then the excess error is close to 0. All right. This also tells us something. We already bounded this error. So, in other words, we automatically have a bound for the error in classification, for the excess error in classification. So, for Lipschitz f, I can just plug in back that bound for the regression part, and I get this bound for the classification part. And the main point being made here is that all the intuition we just developed for regression carries over to classification. Intuition in terms of smoothness and such things, or intuition in terms of the choice of k. It all carries over to classification automatically. All right. Now, classification is actually easier than regression. If I look back at this bound is still telling me that I have a fairly strong dependence on the dimension. Okay, this is not the dimension of the entire, the ambient dimension of the data. It is the intrinsic dimension, but it is still a dependence on dimension. And sometimes we want much faster rates. We want 1 over square root n rates and such things. Maybe if we do linear classification, SVM classification, such things, we often get 1 over square root n. Why can we get that for nearest neighbors? Right. This is telling us that maybe we cannot get that, but it's actually a wrong message. Nearest neighbor classification happens to be much easier. And here I'll give an intuition why. So let's again look at the same cartoon. And now the question, now notice first the following thing. Suppose that f has margin delta nearly everywhere. Okay? F itself is not very close to 1/2. Let's say it's very far from 1/2. If it is very far from 1/2, then what that means is that what that means automatically is that we don't need fk to be very close to f in order for hk to have the same sign as h star. As long as fk is on the same side of 1/2 as f, we have 0 excess error. Okay. So in other words, if fk of f is less than delta, then hk should be equal to h star in this whole region. No need for fk to be very close, no need to do a very good regression. You can just do regression till a certain point, and you already have a very good classifier. That's the whole point being made. So this was formalized, for instance, in works by Odiber and Tibakov, under this sort of noise condition. The noise condition says the following. It just characterizes how often f is higher, has a margin delta. And it says that f often has a margin delta. Every time that condition is broken, that condition is only broken on a very small part of the space. So it's really just characterizing the mass of that part of the space where you don't have margin. And it says that the mass of that part of the space where you don't have margin goes down very quick. And how quick depends on some parameter beta. Now, here is some quick intuition. Suppose this condition holds, right? Suppose this condition holds. And suppose now that fk minus f is known to be less than some delta n everywhere. So this is a regression. Fk minus f is less than delta n everywhere. If it is less than delta n everywhere, then hk is different from h star only if there was no margin. Okay? So the likelihood of error is really bounded by the likelihood of there being no margin. And you automatically then get that the likelihood of error is bounded by delta n to the beta by just plugging that back into here. And if delta n happened to be the error that we had earlier for regression, then that tells us that the error for classification is boosted down by beta. It's already much better. So formally, by following arguments of this type, it can be shown, for instance, that for Lipschitz F, the right rate for nearest neighbor classification is of this form. N minus beta plus 1 over 2 plus d. Earlier, the earlier rate for classification that we obtained was with beta equal to 0. So now look at here. Suppose, for instance, that beta is infinity. what you automatically have is that you quickly have zero error. And beta equal to infinity just means that you have margin everywhere. And for a sample size large enough, you have zero error. There is no curse of dimension. In fact, I don't need beta to be infinity. As long as beta is large enough, it cancels out the effect of the dimension, and you have no curse of dimension. So you have very fast convergence potentially for nearest neighbor classification with not much curse of dimension as long as there is margin. And that's, I think, a beautiful fact. So let me just repeat some of the messages that we've seen so far. The choice of metric is important. The choice of metric affects how smooth the function f is, the regression function is, and it also affects the intrinsic dimension. And how smooth the function is and the intrinsic dimension control how well nearest neighbor will perform. And this is very true in regression. It is somewhat true in classification, but what we just saw is that as long as we have margin in classification, nearest neighbor performs much better and has less, and in other words, the choice of metric becomes less important in classification, which is an interesting message. I'll make some quick technical remarks. Much of the analysis for classification had been done for px uniform, assuming that the density, the distribution of x is uniform on some compact space. And much work still needs to be done for the non-uniform case, and there's been a few quite interesting work so far for the non-uniform case, but we need to explore that area more. I'm putting this here because I know that hopefully some of us here might try to explore this area a lot more. Because in reality, data is nearly never uniform. Okay, we've developed some intuition so far, but we've assumed in the case of classification that we only have two labels. Much of modern classification problems are multi-class. We have multiple labels. And so the question is, does the intuition that we developed so far carry over to multi-class? And it does. And I'll just give an intuition as to why it carries over to multi-class classification. So let's consider a simple multi-class classification problem. Again, handwritten characters. You have 10 classes, 0, 1 through 9. And let's here formally let big L be the number of classes. Again, nearest neighbor does not change. And that's a nice thing about nearest neighbors, that you can do multi-class easily. Unlike support vector machines and other things where you have to do one against all and such things, this is really natural for a multi-class. Now, we want to again reduce this thing to regression. In order to reduce it to regression, now we have to reduce it to vector-valued regression. So let's define fky, where y is a label, y is either 1 through L, fky as the proportion of y equal to y out of the nearest neighbors of x. Okay, so that's a regression function. It's a regression for every possible label. This regressor is estimating this true value, this true regression function. It's estimating p, the probability that y is equal to little y given x. And you can quickly see that the best possible classifier just maximizes this function. It picks the label corresponding to the highest likelihood class, right? And hk of x can be seen quickly to be exactly this. It just maximizes fky of x. So the same type of reduction is possible in multi-class classification. Previous insights will extend. Now we have to redefine the notion of margin. That's the only thing we essentially have to do. Lipschitzness, smoothness, all those things very easily carried through. The notion of margin just need to be slightly redefined. It just needs to be redefined as the margin between the highest probability class and the second highest probability class. Once you do that, all the intuition carries through. And this is how you then redefine the Tibakov's noise condition. The key point here is that understanding binary classification quickly leads you to understanding multi-class classification. You get essentially the same rate through the same arguments as before. The only thing now is that the rate is worsened slightly by log L, the number of classes. However, log L is sort of nice. You can really work with a lot of classes and not worsen the rate too much. All right. So for multi-class classification, however, I believe that one of the glaringly, okay, I don't know how to say this word, glaringly, I don't know. So one of the biggest open problems is the following. It's that in a lot of problems in multi-class, the cost of a mistake is not the same for all mistakes, right? Multi-class with miscost is hasn't been studied as much and needs to be studied a lot more, I believe. In areas such as medicine, finance, not all errors are equivalent. Not all mistakes are equivalent. And here, you can, however, still extend quickly, you can quickly extend a lot of the intuition we developed to the miscost setting by doing the following. For every y, rather than associating the probability of that big Y is equal to little y, you associate the expected cost when predicting Y is wrong. Okay? And then from there, you can build the same sort of intuition. Natural extensions of these type of insights are done in Reeve and Brown 17, but I haven't seen much more work on this. However, the main question for me that remains here is the following. Generally, we don't know this expected cost. In a lot of these problems, medicine, finance, we don't know this expected cost. And I believe that some of the things that have to be done here is how do we access the miscost in multi-class classifications? How do we access it in practice? And how do we integrate that with the practice of nearest neighbor methods? So that sort of covers much of the statistical insights. There is tons more that I wish I could have talked about, but I'll stop here. Okay.
So when you had like little d, your obviously weights depended on that. What if you're on a manifold, like you have this, your data is submanifold, but like the data is sort of noisy about the noise?
Oh, they cannot hear the question, so. I didn't hear it fully either, yeah.
My question is, so if your data is on a submanifold of dimension little d, right, you've got a rate that depends on that. Mm-hmm. If your data is maybe just a little bit above and below that manifold, like in a sort of noisy ribbon, I mean, in principle, your data now is in the higher dimension space, but is it the case that you immediately suffer all the way to big D, or can you somehow interpolate between little d and big D as you sort of get this thicker ribbon?
Yeah. So that's a very nice question. And so I do believe that the right notion of intrinsic dimension remains still unclear. And so let's say the question is, let's say your data lies on a manifold, but not exactly on a manifold, but on manifold plus ambient noise. So if you get in very small regions of the manifold, the whole data looks full dimensional. But if you look at it from afar, the data looks like a line, right? That's sort of the question. So my belief is that what then happens is when you have very few samples, the data sort of looks like a line to you, and you should be converging at rates that just depend on the manifold dimension. However, the moment you have a lot of samples, your nearest neighbor distances get smaller, and you start incurring the effect of the ambient dimension. But I tried to characterize that a bit in some earlier paper, but it's very hard to characterize it properly. In fact, that also touches upon something else, which is that the right notion of dimension should not depend just on the metric or on the support of the data, but should also depend on your distribution somehow. But exact characterization of that, I don't believe has been done. So.
So with regard to the distance function, what happens if your metric properties aren't fulfilled, specifically the triangle inequality? How much of what you presented here is altered?
Okay, that's a very nice question. So the question is, what if you don't have a metric? What if maybe you have some general dissimilarity measure? So the main thing that sort of happens there is, remember the regression analysis. In the regression analysis, you have this variance bias decomposition. The variance part didn't care so much about what metric you had, so you can imagine that the variance part remains somewhat the same. The bias part cared. So let's imagine that you still have some sort of Lifshitzness with respect to your dissimilarity, then much of that will carry through. What will not carry through is the following. It becomes very hard to assess the behavior of your nearest neighbor distances, because assessing that does depend often on essentially being able to characterize what you mean by a ball in the space. So that's the high-level answer. But in some cases, you can still extend much of this analysis. So thank you again, and Sanjoy will be presenting the second part now. I guess we should switch.
Okay. Great. Okay. Okay, so what I'll be doing is talking mostly about algorithmic aspects of nearest neighbor, basically algorithms and data structures for fast nearest neighbor search. But what I'll do first is to just cement some of the statistical issues that Samory introduced. Okay, so I'll be distinguishing three types of nearest neighbor classification. The one nearest neighbor, the k nearest neighbor, where you look at a constant number of nearest neighbors, 2, 3, 5, whatever, and k sub n nearest neighbor, where you let the number of nearest neighbors grow with n. Okay, so these are three different regimes that, that need to be considered separately. Now, so the key object in nearest neighbor, of course, is the distance function. And almost all of the work has really focused on the finite dimensional Euclidean case, okay, both on the statistical and the algorithmic side. Okay? A more general case that's of great interest is when the distance function is a metric. Okay, so it's symmetric, it satisfies the triangle inequality. Okay? And this is a big jump. There are many things that work in Euclidean space that break when we move to the metric setting. And we'll see some examples of that. Okay? And then there are lots of distance functions that we'd like to use that are not metrics at all. Okay? And a prime example of this is KL divergence, which is not even symmetric. Okay? Or in fact, any number of domain-specific distance functions. Okay? So we'll be looking at methods that work in these three different regimes. So let's start by talking a little bit about the statistics of nearest neighbor, and this is really just to reinforce a couple of the points that Samory was making. Okay, so we have some data space, and let's say it's a metric space, so we have some metric row. And then there's some distribution on this space from which the data is generated. I'll just be calling that mu. So that tells you how you get the x's. X's are generated from mu. And now each x has a label. For simplicity, let's say the labels are binary, 0 or 1. And for any given x, there's a probability of it being 0 or 1. Okay, so you can imagine that the way a point is generated is that it's sampled from this distribution mu, and then a coin is flipped with this particular bias, eta of x. Okay, and that tells you whether the label is going to be 0 or 1. So this is a little weird. You know, why is this stochastic? The label is either 0 or 1. Why are we introducing this kind of randomness over here? And, you know, it really depends on the type of data. If you're dealing with MNIST, then, of course, given a specific image, it's a 0 or a 1 or a 2 or a 3. There's nothing random in it. But in other kinds of data, there is inherent stochasticity. For example, suppose you have a medical prediction problem where the X is somebody's medical record and the Y is whether they're going to get ill, whether they're going to get seriously ill next year. There just isn't enough information in X to be able to uniquely, deterministically specify Y. And in those cases, there really is some probability of either outcome. So the case of a stochastic eta, this conditional of a stochastic conditional probability over here is an important case. And so a lot of the work has been interested in getting this right. And that's why it's built in to the statistical learning framework. Okay? So clearly, the best thing you can do for any x is just to predict 1 if the probability of being 1 is going to be greater than a half, and to otherwise predict 0. Okay? And so that's the Bayes optimal classifier, and R star is the error obtained by this optimal classifier. Okay. So one of the questions that we can afford to ask about a non-parametric method is whether it converges to the optimal possible error. Okay, so obviously this is not something we can expect of a linear classifier or something like that. But when we have a non-parametric method, one that has a potentially unbounded number of parameters, there's the possibility that it will be able to fit any decision boundary no matter what. Okay? And so, and that's called consistency. And the first sort of basic fact about nearest neighbor is that one nearest neighbor is not consistent. And here's an example, okay? So let's say the data lie on the line, so x is r, and the label at any point is a coin flip with probability a quarter. Okay, so at any given point, the label, you just toss a coin, and with probability a quarter, it's 1, with probability 3/4, it's 0. So clearly, the best prediction is just to say 0 everywhere. That's the optimal thing to do. But that's not what one nearest neighbor is going to do. One nearest neighbor, a quarter of the time, is going to have a label of 1. Okay? So one nearest neighbor is suboptimal no matter how many data points you have. So consistency fails in this case. And in fact, the same example shows you that k nearest neighbor is not consistent either. Okay? So in situations where this eta function is not deterministic, it's not always 0 or always 1, you have to look beyond one nearest neighbor or k nearest neighbor. Okay? And then you move to this general k sub n nearest neighbor where you let k grow with n. Okay. So, one general question has been, what are the minimal conditions we need for consistency? And I'll say a little bit more about that. And then, of course, there's the rates of convergence, which is what matters for a finite data set. And ultimately, they depend on the smoothness of this eta function, the smoothness of the decision boundary. Is it a nice, simple decision boundary, or is it really jagged? Okay, and there are different ways of quantifying this. Okay, so Samory went over this argument essentially from the 1960s that nearest neighbor is consistent in metric spaces provided this eta function is continuous. So this function, this conditional probability function, this coin toss probability, if it's continuous, if similar points close together have similar coin toss probabilities, then nearest neighbor is in fact consistent in metric spaces. And this was proved by Cover and Hart. Okay. But we'd like, ideally we'd like consistency to hold without any assumptions whatsoever. We have no idea if the eta function, in our particular application is going to be consistent or not. And so it was a huge result in the 70s when Stone showed that nearest neighbor is consistent, and now we're talking about k nearest neighbor, where k grows with n, the nearest neighbor is consistent without any assumptions at all. Okay? And I'm not going to go through the result. It's actually not complicated. But what I will do is to go through the one central mathematical fact. And the reason I'll go through that is because, this fact came up first in Stone's proof, but it turns out that it comes up again and again when you're looking at algorithms for nearest neighbors, when you're looking at analysis, statistical analysis of nearest neighbors. And it's this geometric question, okay? So here's the question that's sort of at the heart of this consistency question. Suppose you have n data points, and you choose one of them. For how many of the remaining n minus 1 points can this be the nearest neighbor? Can it be that this is the nearest neighbor of all the remaining n minus 1 points? That's the question, okay? So you have n data points in your space, okay? You choose any one of them, and for how many of these points can this particular point be the nearest neighbor? And it turns out that the answer is a constant number. No matter how large n is, any one point can be the nearest neighbor of at most a constant number of points. Okay? And I'll just briefly explain why this is the case. Okay? So to explain this, what we do is we look at cones. Cones that are subtended at this particular point, cones whose tip is this particular point, and then they stretch out to infinity. And each cone is very thin. The angle of the cone about its central axis is, say, 10 degrees. Okay, so each cone is thin. And we have enough cones to cover the entire space. How many cones do we need? Well, it's basically asking how many spherical caps of constant radius do we need to cover the surface of a sphere. And so the number of cones we need is about 5 to the d. Now, within each cone, how many of the points that fall in this cone can have this as its nearest neighbor? Only one of them. Only the very closest one. Because the cones are so thin that other points, like this one, will actually be closer to this than to the red point. And so by this particular argument, this is how one resolves this issue. And this comes up over and over again, okay? Now, unfortunately, it turns out that in metric spaces, this no longer holds. Okay? So this argument fails in metric spaces, and this is why, for a lot of the statistical work, as well as for algorithmic work, one often has to look at very different methods. Okay? Why metric spaces often demand a different method. Okay, so this was Stone's result. It's a really glorious result from the 70s, and it applied, however, only to finite dimensional Euclidean space. And so the question after that was, what about other spaces? What about general metric spaces? Is nearest neighbor consistent in metric spaces if one doesn't assume stuff like continuity? And the answer is that it's not. You can come up with some really weird metric spaces, which are genuinely pathological, in which nearest neighbor is not consistent. Okay? But at the same time, there's been an effort, and it's continuing, to try and identify conditions on the metric space under which you do get continuity. And basically, the most general condition known so far is a metric space that satisfies essentially the fundamental theorem of calculus. So the fundamental theorem of calculus is that differentiation is the inverse of integration. If you take a function and you integrate it, and then you take the derivative, you get the original function back. So you can write the metric space version of this. This is what it looks like. And if the metric space satisfies that theorem, then universal consistency holds in that metric space. Okay, I'm not going to go into the details of that. Okay, but it's a very different kind of argument for consistency. And we know lots of families of metric spaces. It's hard that satisfy this. It's hard to cook up a space that doesn't satisfy this. Okay, so this is the current state of consistency. Okay, so that's consistency. I won't go through the argument. Now, in terms of rates of convergence, the bad news, as we've seen, is that like any non-parametric method, there's a curse of dimension. The good news is that nearest neighbor is adaptive to intrinsic low dimension. And this is something that we'll formalize when we start talking about algorithms. What is a notion of intrinsic low dimension that can apply in many settings? Okay? So Samory went through some of the bounds. And the one thing I'll say is that you can give bounds for nearest neighbor without any requirements. Okay? You don't need to assume any kind of smoothness or anything. You can give rates of convergence, but they don't look pretty. Okay? If you want bounds that look nice, you start introducing smoothness conditions. You say, oh, it's not just continuous, but it satisfies these kinds of properties. It's Holder continuous. The boundary, the margin has a certain behavior. And these are conditions that were developed in the statistical literature for non-parametrics in general. And it was shown by Audibert and Sibakov that for any method, there are some basic lower bounds on the achievable rates. Okay? And it turns out that nearest neighbor achieves these rates. So as far as non-parametric methods go, it gets the best possible rates under these smoothness assumptions. Okay? And so it's a nice method. Okay. Okay, so I won't talk too much more about rates. Now, so one question one can ask now is that, okay, we have an idea of the convergence behavior of nearest neighbor. We know it's consistent. We know what kind of rates it attains. Now that we know this, can we come up with variants that shrink the data and are therefore computationally more reasonable and yet have the same rates? Okay? So can we come up with something that makes life algorithmically easier for us and yet demonstrates all this good behavior, universal consistency, the nice rates, and so on? And there are two broad families of strategies for this: quantization methods and subsampling methods. And so let me just talk about these. So what happens in a quantization method is you start with a humongous data set, but then you just throw away most of the points, okay? And you just keep a few, and you do nearest neighbor just on those. But you pick those points carefully so that you get good rates of convergence, okay? The same rates you were getting with nearest neighbor on the original data set, okay? So the idea is you've got this big data set. You pick a few of the points, which are shown here in yellow, okay? Those are the only ones you're going to keep. Let's call them Q. Everything else is going to get thrown away. But before we throw the other stuff away, we assign each of them to their closest selected point, to their closest center. It's sort of a Voronoi partition. And we replace this guy's label with the average of their labels. Okay? So we keep just a few of the points, but we tweak their labels. We replace their label with the average label of all the points that were assigned to them. Now, when it comes time to classify a new point, we just pick the closest, either the one nearest neighbor or k nearest neighbors of the few points that remain. Okay? And so there's been some really nice work on this. For example, Samory and Verma looked at a construction where the set Q is an epsilon net of the space. Okay, so you pick a point, you pick any point that's epsilon far from it, another point that's epsilon far from those two, and so on. And they showed that the empirical performance of this is very good. And they showed, in fact, you can get optimal rates if you assign each of these points Q a weight proportional to the number of points that were allocated to them in their Voronoi partition. There's been some very nice work by Arya Kantorovich, Roy Weiss, and Sivan Sabato, where they also pick Q to be a kind of epsilon cover. And they show that doing one nearest neighbor on Q is consistent, even though one nearest neighbor in general is not consistent. Okay? So if you remember, the reason one nearest neighbor in general is not consistent is because of stochasticity in the label. But here we've changed the labels to be the average of all the points allocated to them. And so that consistency problem goes away. Okay? So these are some nice quantization methods. Another approach, which is very amenable to parallelization, is to basically do a kind of bagged one nearest neighbor. Bagging with one nearest neighbor. Okay? And so the idea here is now you have this huge data set, and you randomly just pick 1/10 of it. Okay, so you pick 1/10 of the points at random. Then you randomly pick 1/10 of the points, and let's say you do this like 5 times. You can assign them to different processors if you like. And now when a new point arises, you just find its nearest neighbor in the first group, the nearest neighbor in the second group, the nearest neighbor in the third group. Okay, just the one nearest neighbor. And then you take the majority vote of those 5 groups. Okay, so it's a very simple idea. You've shrunk the data set by a factor of 10. You can separate, maybe you have 4 or 5 groups. You separate them out among different machines. You're just doing one nearest neighbor each time, which is simple. And it's been shown by these various authors that first of all, this is consistent even though it's one nearest neighbor. Okay? So doing this kind of bagged one nearest neighbor is consistent. And in fact, you can think of it as a kind of weighted k nearest neighbor. Because if you look at the k nearest neighbors of a query point in the original data set, there is some probability that any one of those k nearest neighbors will be the one nearest neighbor of the point in one of these subsample data sets. And that enables us to think of it as a sort of weighted k nearest neighbor. Okay, and asymptotically, this turns out to actually be more accurate than k nearest neighbor. So it's kind of an interesting method. It's got good theoretical properties and good empirical behavior. Okay. Okay. So now I'll talk a little bit about, so that's it for the statistical approaches. And now I'll talk a little bit just about fast nearest neighbor search in general. And some ways of thinking about algorithms for this problem. Okay, so we're in some metric space. Okay, we have n points. We get a query. We want to find the nearest neighbor, and of course, brute force takes time proportional to n. So that's bad. We want to be able to do something faster. So what we would like is to take those points and come up with a data structure that's of linear size. We don't want a huge data structure, such that queries can subsequently be answered in time little o of n, much faster than n. Okay? Now, the case in which we can really do this very easily is if the points lie on a line. Why? What's the data structure? Well, if you have n points on the line, just sort them. So your data structure is just the sorted list of points. And now when you get a query point, you do binary search and you find the nearest neighbor. Okay? So if the points lie on the line, you can get a data structure size of O of n and a query time of log n trivially. Okay? So the question is, can we do something like this in a metric space? Or in fact, can we even do something like this in a higher dimensional Euclidean space, in d-dimensional Euclidean space? And if we can do it, how does the d come in? Does the query time become d log n? Or does it become 2 to the d log n? Or what is the dependence on the dimension? And unfortunately, the dependence seems to be exponential in the dimension. Okay? So behind a lot of the work in fast nearest neighbor search, there is this unproven but very common conjecture that something exponential in the dimension is going to creep in. And the reason, the reason why people think this is because of a particular bad case. Okay, and so let me tell you what it is, okay? So let's say that we're in d-dimensional space. And the points are chosen at random from the surface of the unit sphere, okay? So we're in d-dimensional space. We pick points at random from the surface of the unit sphere. One of the weird things about high dimension is that you can pick about 2 to the d points. If you pick points at random, you can pick about 2 to the d points, and they'll all be roughly the same distance from each other, okay? That's bad, right? So the typical distance will be square root 2, and the points will all be between 0.99 square root 2 and 1.01 square root 2. So now you get exponentially many points, 2 to the d points, that are all almost exactly the same distance from each other. And you have another point that's of this type, and you want to find which one's the closest one. And they're all almost exactly the same distance. It seems like there isn't an easy way to pick out the closest one easily. And so this is, as far as I know, this hasn't been made into a concrete lower bound, but this is a bad case to keep in mind when you're thinking about nearest neighbor data structures. This is the nightmare scenario. And the question always is, what is it about our data or about the way in which we're doing things that we're able to override this nightmare scenario? Okay? So, and I'll be talking more about, there are basically two strategies. The first is, you say that the data seems to be in a high dimensional space, but actually it has intrinsic low dimension. So we're exponential, but only in that intrinsic low dimension. And then we'll look at some definitions of intrinsic low dimension. And the second is to say that, well, we don't want the exact nearest neighbor. If you have 2 to the d points that are all approximately the same distance, just pick any of them, I don't care. Okay? So these are the two ways that people have thought about to get over this problem. And so we'll look at the kind of strategies that these lead to. Okay? So, so let me just give you a brief history of nearest neighbor search methods. The mother of all nearest neighbor data structures is the KD tree. And this was introduced in 1975, in the 70s, by Bentley and Friedman. A beautiful, simple data structure, still very widely used, and still poorly characterized. It seems to work very well sometimes, not so well other times. Sometimes it works well in high dimension, sometimes it doesn't. There isn't really a very nice characterization of when it does well. And it's for data in Euclidean space. So then in the 80s and 90s, people said, this KD tree is really nice, but it's only for Euclidean data. What if we were in a more general metric space? What kind of data structures could we come up with then? Okay? And they started developing all sorts of clever tree structures. Okay? So that was sort of a second phase of nearest neighbor Okay? The third phase was randomization. And this made a huge difference. So the idea was, you know what? We can have a randomized algorithm, and it's allowed to fail sometimes. And just giving oneself a little bit of slack like that turned out to make a huge difference and has led to all sorts of very effective data structures. And we'll go over that. One prime example of such a data structure is locality-sensitive hashing. I'll go over that. And more recently, there has been a resurgence of tree structures and an interest in binary hashing, and I'll say a little bit about that too. Okay, so the KD tree. Let's start with that one. Real basic, okay? You have points in Euclidean space. You pick a coordinate. You split the points along the median of that coordinate. So you pick one coordinate, you compute the median, you split the points in two, and then you recurse on the two halves. And in this way, you get a tree structure. Which coordinate do you pick? Typically the one on which the stretch is the most. And you define it however you like, okay? Okay, so that's the data structure. There are two ways to search using this data structure. The first is the quick and dirty way called defeatist search. So given a query point, you just move it down the tree, and you look at the box that it ends up in, and you just return the nearest neighbor in that box. Okay, so how long does that take? It takes log n to go down the tree, and then however many points you have in that box. Okay, so let's say you grew the tree until you had 1,000 points in each box. Okay, so then the time is log n plus 1,000, because you compute distances to those 1,000 points. The problem is, maybe you'll get the nearest neighbor and maybe you won't. Because, if the point is, for example, over here, then the nearest neighbor might be that one, okay? And which is in a different cell. So the other method, which is sort of the more careful one, is called comprehensive search, where you start with the defeatist search. So you start with this point and you say, oh, well, defeatist search tells me the nearest neighbor is that, but I'm so close to the boundary that the nearest neighbor might actually be in this adjoining cell. And once you're looking at that adjoining cell, you say, oh, it might actually be in that adjoining cell, and so on. And so you might eventually end up looking at all the points if you're unlucky, okay? But you always get the right answer. Okay. So these are the two ways of dealing with a KD tree. And then people said, okay, let's do this for more general metric spaces. But now there's no notion of a coordinate any longer. So how do we split? We can't just say we split along a coordinate. So one idea is called the ball tree, where you say, well, if we're in a metric, we still have this idea of a ball, okay? So what we'll do is that we'll take our points and divide them into two balls. And the balls might be overlapping, but every point goes to one ball or the other. And then we recurse on the two halves. And in this way, we get a tree that's basically a nested collection of balls. Okay? And to search, you can, again, either do defeatist or comprehensive search. Okay. Now, one interesting thing here is that these have been extended even to non-metric spaces. Okay? So one family of distance functions that includes a lot of non-metric distances are the Bregman divergences. These are the distance functions associated with exponential families of distribution. So they include the KL divergence, squared Euclidean distance, a whole bunch of other distance functions that arise naturally in statistics. And people have shown that these kinds of distance spaces have enough nice properties to actually permit data structures of this kind. Okay? Another variant on this, a vantage point tree, where instead of having two balls, you have just one ball and the outside of the ball. Okay? So you pick a point, you grow a ball until you get half the data points, and then one side of the tree gets the points in the ball, the other side of the tree gets the points outside the ball. Okay, so there are all these data structures. Many of them are built into Python. You can just use them, highly effective. But the not so nice thing about these structures is that there are very few guarantees for them. And it's not because guarantees don't exist, it's just that people really haven't gotten around to it yet. Okay? So right. So let's talk about data structures that actually can guarantee something about the query time. Okay. And as I said, there's this bad case, which is points uniformly spread on a unit ball, and there are two approaches to getting around it. Either you say that somehow the data has low intrinsic dimension, or that you don't care about getting the exact nearest neighbor, and an approximate nearest neighbor is okay. Okay? So in terms of methods that adapt to the intrinsic dimension, in the 90s, there was a lot of work on this by Ken Clarkson. And this was picked up by various people in the CS theory community, like Robbie Krautgamer and James Lee. And one nice data structure of this type was developed by Alina Bagel-Ziemer, Sham Kakade, and John Langford. And it's called the cover tree. Okay, and this is something that works in a general metric space. And so I'll just say briefly what it is. It's a tree, okay? And each node of the tree is associated with a data point, okay? And let's say the data has diameter 1. Then the top node is a 1 cover of the data points. Everything's within distance 1 of it. At the next level, the points are a half cover of the data. Everything's within distance half of one of these points. The next level is a quarter cover. Everything's within distance a quarter. So it's a very organized hierarchy. Okay? And it turns out that you can build these in a way that permits dynamic insertion and deletion. The whole thing takes space O of n. And the query time turns out to just be some constant times log n. Okay? So the query is done by comprehensive search, and the levels of the tree can contain a lot of nodes, but it turns out that as you go down the tree, you only have to look at a constant number of nodes. So at any given level, you can eliminate all but a constant number of nodes just by geometric considerations, okay, by the distance and by invoking the triangle inequality, essentially. Okay, so you can go down the tree, and at each stage, you're just looking at a constant number of nodes. So what is this constant? It's a fairly big constant. It's called the expansion rate of the metric space. Okay? And so what is this expansion rate? It says that, well, if you look at any ball, and you look at the number of points that fall in it, and now you double the radius of the ball, the number of points in the bigger ball is at most c times the number of points in the original ball. Okay, so the number of points goes up by a factor of at most c. So if you're let's say you're in d-dimensional Euclidean space, and you have the uniform distribution. If you double the radius of the ball, the number of points in it is going to go up by a factor of 2 to the d. So this constant is basically exponential in the dimension. You can think of it as exponential in some kind of notion of intrinsic dimension. So we haven't been able to get rid of the exponential in dimension thing, but this is a notion of intrinsic dimension, okay? And in a little bit, I'll formalize another slightly better notion of intrinsic dimension, okay? So this is great. It's something that works in an arbitrary metric space, and it adapts to intrinsic dimension, okay? So once this was introduced, the natural question was, well, you know, very often data is Euclidean. Is there something even easier than this that we can do for the Euclidean case? Okay? And so, and there are a couple of things one can use in that case, and a simple example is the random projection tree, which is a lot like a KD tree. But instead of picking a coordinate direction at each stage, you just pick a random direction from the surface of the unit sphere. So instead of saying, I'm going to split along the x1 coordinate or the x2 coordinate, you just pick a direction at random, and you split along that direction. And instead of splitting exactly at the median, you split between the 45th and 55th percentile chosen at random. Okay? So, what can you show about this? You can show that, well, you can just do defeatist search on this structure, so it's very fast. And if you do that, the failure probability is at most a half on any query, as long as each leaf has got a substantial number of points, where that number of points is exponential in the doubling dimension of the data. Okay, so there are two things going on over here. This is one of those data structures that has a failure probability. Okay, so it returns a point, but it might not be the nearest neighbor. But you know that the failure probability is less than a half. And so what you can do is to just build many trees. Okay, so you build 10 trees, and then the failure probability becomes 1 over 2 to the 10. Okay, because each of them returns a nearest neighbor, and you just choose whichever was the closest out of those 10, and the failure probability drops. Okay, so once you have a failure probability that applies to a specific instance, that by any specific instance the failure probability is less than a half, then by duplication, it's possible to drive down the failure probability very rapidly. And this has been sort of a basic insight of a lot of nearest neighbor methods. Okay? The second thing going on over here is that, so the time complexity to answer a query is log n plus the number of points in a leaf. And the number of points in a leaf is exponential in this doubling dimension. And what I'll do now is I'll just spend a little bit of time talking about the doubling dimension because, you know, a lot of different notions of dimension have come up in developing nearest neighbor algorithms, okay? Because one really wants to adapt to intrinsic dimension. And this, in a sense, is the one that has been the most compelling in terms of how general it is and what it permits algorithmically. And so, you know, if one had to pick one notion, this would probably be the one. So I'll just spend a couple of minutes on it. So what is this? What is the doubling dimension of a metric space? So it's something you can define for any metric space. But suppose we just, to keep things simple, we're just looking at points in Euclidean space. And we have a bunch of points in Euclidean space, in d-dimensional Euclidean space. And somehow we think that the intrinsic dimension of these points is much less than d. Okay? What is the right notion? Okay? So we say the doubling dimension is d0 if any ball b can be covered by 2 to the d0 balls of half the radius. Okay, so it sounds a little weird, but let's look at an example. So let's say you have a line sitting in some high-dimensional space. Okay? So look at any ball. The points lying in the ball is this line segment, and they can be covered by 2 balls of half the radius. And so the doubling dimension is 1. Okay? So a line has doubling dimension 1. A k-dimensional subspace has doubling dimension O of k. The doubling dimension gives you bounds on epsilon covers. Okay? So if you have doubling dimension d0, you have epsilon covers of size 1 over epsilon to the d0. And it turns out that sparse sets have low doubling dimension. Okay, so for example, let's say you have data where the dimension is very high, but on any given data point, just a few coordinates are set. Then you can argue, I won't go through the proof, that the doubling dimension actually is just linear in the sparsity, the number of non-zero coordinates, and logarithmic in the ambient dimension. Okay, so it's a notion of dimension that captures sparse data. And it's also a notion of dimension that captures manifold structure. Okay, so you can say that if you have data that lies on a manifold of dimension k, then the doubling dimension turns out to again be O of k in neighborhoods of the data set. Okay, so it's a notion of dimension that captures a lot of the kinds of intrinsic low-dimensional structure that we're familiar with. And so, and this is what sort of made it compelling. Okay. Okay, so now, so we've talked a little bit about methods for doing nearest neighbor search where you are trying to just be exponential in the intrinsic dimension. Okay? What about methods where you don't, so the second approach is to say, well, we don't actually need the exact nearest neighbor. We're okay, we're comfortable with an approximate nearest neighbor. And this paradigm was introduced by Indik and Motwani. Okay? And the algorithm or the framework they came up with is locality-sensitive hashing, which has been an extremely powerful framework for nearest neighbor search. So here, the nearest neighbor data structure is built by hashing, but not just typical random hash functions, but rather hash functions that preserve locality. Points that are very close together are likely to hash to the same bucket. Okay, so that's what locality means. So here is the most commonly used hash function for locality-sensitive hashing. It's a random linear function that's then binned into bins of fixed width. Okay? So to specify the hash function, you choose a random direction and a random offset. And given a vector x, you take the dot product with that direction and you add the offset. So you compute a random linear function. Okay? So that gives you a real number. And then you take those real numbers and you divide them into bins of fixed width. And so each point maps to an integer. Did it fall into bin number 1? Did it fall into bin number 2? Did it fall into bin number 3? So a point gets hashed to an integer, and points that are really close together are likely to map to the same integer. So that's one hash function, but then you do it multiple times. You have one hash function along this axis, another hash function along this axis. And so if you pick k hash functions, you end up with a k-dimensional table, where each point maps to one cell of the table. Now, it sounds like these tables would get very large. If you have a k-dimensional table, it sounds like the size would be at least 2 to the k. But you don't have to store this table in explicit form. You can just take this k-dimensional representation and then use a standard hash function, a standard random hash function, to map it to a hash table of size n, where n is the number of data points. Okay? And now, to answer a query, you just look at the cell into which it hashes and look for the nearest neighbor in that cell. And what they showed is that if you do this, then the probability that you fail to return an approximate nearest neighbor, and I'll say what that is less than 1. Okay? Let's say it's 0.9. And that's exactly what we need. Okay? Because this holds for any query. So you just need to build a whole bunch of tables. You build 10 tables, and the probability becomes 0.9 to the power of 10. Okay, you build 100 tables, it becomes 0.9 to the power of 100. Okay, so as long as, this randomization paradigm has been very effective because you can make the error probability as low as you like by just duplication. You know, it's a very simple operation. Okay, okay. So what do I mean by approximate nearest neighbor? Well, basically, a C approximate nearest neighbor is one that is at most C times as far away as the closest point. Okay, so if the closest point is distance 10, then you return something that's a distance at most 10C. Okay, so if C is 1.1, then you return something within distance 11. That's what C approximate means. And what they've been able to show is that if you're doing nearest neighbor search in Euclidean space, you can get a query time of n to the 1 over c squared and a data structure size of n to the 1 plus 1 over c squared. So let's say you're doing 2 approximate nearest neighbor. You get a query time of n to the quarter, and you get a data structure size of n to the 1.25, n to the 5 fourths. Okay? So, okay. And this is just for Euclidean space, but hash functions have been developed for all sorts of other spaces as well. So one of the interesting open problems here is that you know, this quantity C is something very mysterious because it means different things for different data sets. Like, what is a C approximate nearest neighbor? What C is good? Is C equal 1.1 good? Is C equal to 2 good? Is C equal to 3 good? What's the story over here? Okay. So like if you look at MNIST, for example, this is an easy data set, right? Like, what kind of value of C would we want here if we were doing C approximate nearest neighbor? Well, so here's a little experiment you can do. You can say, well, let's look at C equals 1. That means you get the nearest neighbor for sure, okay? And look at the classification error of one nearest neighbor using that, okay? And that turns out to be 3.1%. I think many of you have probably done this exact exercise, right? One nearest neighbor on MNIST is 3.1% error. Let's say we look at a 1.2 approximate nearest neighbor. What does that mean? Well, there's maybe 100 points that are 1.2 approximate. Let's say you average over them, or you pick one at random. The error shoots up to 9%. Okay, so the performance drops fast. 1.4 approximate, the error goes up to 18%. Okay, now a priori, it would have been impossible to figure out what the right value of C is for this data set. But looking at this, it's clear that you really don't want C more than, say, 1.1. Okay? And yet, if you look at the query time and the data structure size that you get for C equals 1.1, it's almost linear query time and quadratic data structure size. Okay? So, so the weird thing over here is that this method has been motivated from an approximate nearest neighbor viewpoint. But it also does really well on exact nearest neighbor search. So with high probability, it's actually returning the correct nearest neighbor, not a C approximate nearest neighbor at all. And I think it's an interesting problem to just investigate this aspect of LSH, to say, let's forget about all this approximate stuff. We want the nearest neighbor. It really does seem to be giving us the nearest neighbor. What is that? What is the failure probability of that? And I think that might lead to a more interpretable theory for this kind of method. Okay, so one of the so one of the sort of if you had to compare two different families of methods, one reasonable thing to look at would be LSH tables. So LSH is something you build a table and then you do it 10 times. So you have 10 tables. And you can similarly use a randomized tree and build a forest of these trees and compare which is better. Okay? And this is, there have been, there are increasingly sort of studies of this type. Here's one example, and it's, I think it's hard to tell. It's really a toss-up. Okay, so that's all I'm going to say in terms of algorithms for nearest neighbor. So Samory and I have been talking about all sorts of aspects of nearest neighbor, statistical issues, algorithmic issues. If you're interested in finding out more about nearest neighbor, there are these two books that you could look at that are both fairly recent and both 100% devoted to nearest neighbor. The weird thing is that they're actually fairly narrow in focus. For example, they're both focused on entirely statistical questions. And so, in fact, the two of us are planning to soon release a monograph that's hopefully very short, that is sort of a broader survey that includes all the algorithmic stuff and just a broader range of material. Anyway, that's it. Thank you. Yeah.
My question is related to the cover tree. You may not have mentioned it, but the cover tree can be built one point at a time, forming a nice graph. The question I have is, if you permute the sequence of points, you end up with slightly different topologies, different graphs. Has there been any study with regard to the equivalence of those trees?
Right. No, as far as I know, apart from the general guarantee that the search time is bounded in a particular way, it may well be the case that some sequences of insertions lead to a more fortuitous tree than others. And so in particular, if you started with a data set and you were going to build the tree by adding 1 point at a time, and you wanted to say, hey, what's a clever way to do this? I don't know what that would be.
I guess you can find counterexamples if you build them, but in general, wouldn't it be better to use singular value decomposition if you have a cloud of points and you want to choose the major directions, like in the Kpotufe method?
Okay, so let me just repeat the question. So the issue is that, look, we looked at some of these tree structures, like the KD tree and the random direction tree. Why not just pick a direction by principal component analysis? So it turns out that that's something that has been done. It's a study that's been done, and it works better. Let's call it the PCA tree, the principal component analysis tree. It's better than the KD tree, and it's better than a random tree, than a random direction tree. The story changes, however, when one looks at forests. The nice thing about a random tree is that you can build 10 of them, and that's not something you can do when you're using eigenvector directions to make the splits. So I think a very interesting question is, can you do something like a PCA tree, but inject enough randomness into the choice of directions that you would actually be able to build a forest to then drive the error down exponentially fast?
I have a question regarding that very bad situation. You said that all the distances are almost the same. Do you think that it's an interesting case to study? Because I don't know how often it can happen in practice.
Right.
Because then distance is just a number, and triangle inequality holds, but it doesn't give us anything.
Right. So I think the hope of all this work on low intrinsic dimension has been to sort of basically address that intuition that, this bad case is pathological. And in fact, data always has some structure. It doesn't look like, random points on a unit ball. It's got some structure, and and can we formalize types of structure that really move us very far from that case? And one example is the low-dimensional manifold. So the doubling dimension, I think, is a nice encapsulation of many cases that keep us far away from a uniform distribution on a high-dimensional sphere. Has got doubling dimension, whatever the high dimension is. So.
Given what you explained, does it mean when the intrinsic dimension increases, then practically it's impossible to calculate that on small devices? We necessarily need huge servers.
So is the question that that the data structure size increases exponentially in the intrinsic dimension?
Yeah.
Right. Yes. So I don't know ways of getting around that.
Okay.
Other than that's a good point.
So in production for computer vision indices of very large size in last year, one thing that has been working really well is something called hierarchical navigable small world graphs, HNSW. And they seem to be getting good measure on good performance on benchmarks in CV, which is kind of it's a weird cross between skip lists and quantization methods. From your guys' perspective, from the machine learning theory perspective, have these methods not kind of entered your part of the universe yet? Because practically they seem to be the current king of the hill in terms of performance and scaling.
Yeah, I mean, basically right. So the methods that dominate in a particular application, sometimes vary from domain to domain, and also from the specific size of the data set. And so, in terms of the theory work, the idea is to just identify general principles that can, it's hard to. So for example, we were talking about trees versus locality-sensitive hashing, and people in some areas are convinced that locality-sensitive hashing is better, and in a different domain are convinced that trees are better. And the competition, I think it's a bit of a toss-up, and one just has to try. But I will look into those. Navigating small world nets, huh? Okay.
Hi. All this, what you told, suggests somehow that you can use things like looking at balls around points to infer something about the dimension of the data, like as a sort of hypothesis test of what is the actual intrinsic dimension of the data. I know of some of the works about that, but I wanted to know if this has been like studied enough, or is it sort of answered the question whether or not you can use these intuitions about how far points should be away to estimate sort of the dimension of the data?
Right. So in terms of these methods, none of them fortunately require an estimate of the intrinsic dimension. Whatever the intrinsic dimension is, they just adapt to it. But it does raise the question of, if you wanted to estimate the intrinsic dimension, how would you do that? And, this is something that various people have looked at. The typical thing, for example, here's a typical approach, is to run k-means for different values of k and look at the cost that you get, sort of plot the cost against, put them on a log-log scale and look at the slope and stuff like that. And it often turns out to be the case that the dimension actually behaves differently in different parts of the space and at different scales. The dimension is scale specific. So Arthur gave an example earlier of a data set which from far away looks like a low dimensional manifold, but when you get close to it, the noise makes it look full dimensional. So, in terms of mathematical models that can nicely incorporate those sort of features, it's something that's definitely a research area.
Hi. I have a question about the theoretical view on the data structures. I think it's often assumed that accessing a point has the same computational costs in a tree, or it's an array structure or whatsoever, while in most computational units, if we have an array, we can use caching because we can guess locality, while if it's a tree, the point could be anywhere in the RAM, so caching might not work. So this uniform assumption about the costs to access something in the big O notation or something doesn't hold. Do you think there's some work happening looking more on the practically effects of different data structures for the computational costs?
Right. So I think that So that's a valid point. So I guess the issue is accessing a point. Does it have a constant cost or a logarithmic cost? And it might depend on the. I know of a little work on this kind of modeling, but not a huge amount.
Yes, in presence of class imbalance, does quantization still work, or don't you end up getting rid of some of those precious data points that belong to the underrepresented class?
Right. Right. So I guess in that case, one would want to do a class-specific quantization. Since you do have the labels of in that particular setting, you do have the labels in advance. Yeah. Yeah, you can just shout it out if you like.
Approximation, and I have a data structure that's n to the 1 plus 1 over c squared size, what's the best query time I can hope for?
I don't know of bounds of this kind that are, fully general, rather than restricted to, say, an LSH family.
Can I ask the question to the Samory?
Yes.
Yeah, I'm listening.
Yeah, thank you. As you explained, the non-parentic analysis of the k-mean, k-nearest neighbor will produce the rate. It depends on the dimension. But as I remember that uniform stability analysis of the k nearest neighbor, will produce the stability upper bound that the nearest neighbor stability only depends on the one over the sample number. So I think it will produce a better bound. So can you explain the relationship between the uniform stability bound and the non-parentic analysis of the k nearest neighbor?
Which stability bound are you referring to? So,
as remember, there is a uniformity stability bound in the very basic, how to say, the classical paper published in the 2002 by the Bosquet and Elizev.
Okay. So I haven't. Personally, I haven't explored the relationship with that. I do know that some of the recent work so for instance, on one nearest neighbor quantization that Sanjoy referred to actually goes through stability analysis. And when you do look at, much of that work is in terms of tries to establish consistency of these methods rather than rate of this method. And so it is not so clear how the rate relates to intrinsic dimension in these cases, but since there is no actual rate. But I definitely agree with you that it probably needs to be explored, the consistency, the stability properties as it relates to nearest neighbor itself. But we can talk a bit more offline.
Thank you.
Mm-hmm.
So I think there's no further questions, so let's thank the speakers again.